Hey class, and welcome to my classroom, at least for the beginning of this video. So in this video, we're going to take a look at gases. In this unit, we're going to look at gases, solids, and liquids, but first up, gases. You're going to understand the characteristics of gases, the gas laws, and related content like what can we do with them? Kinetic molecular theory of gases, what's the difference between effusion and diffusion, and ideal gas behavior and non-ideal gas behavior. And we'll take a look at some of these a little bit more in depth in the class with some Pogles and some problem solving. Let's go ahead and take a look at characteristics of gases. They are made up of only non-metals. And they tend to have very simple molecular formulas. Think about O2 or N2, and they tend to have low molar masses. Now, a gas will expand spontaneously to fill the container. Liquids and solids cannot do that. They're also highly compressible. That means we compress them. And I always picture like a balloon or a sponge, and you can squeeze it and compress the gas. Go ahead, try to compress that table in front of you. Kind of difficult to do. Solids are the opposite. They don't expand, they are not compressible, at least not with equipment that we have. When you have two or more gases in a mixture, we call that a homogeneous or homogeneous mixture because they're all gases. And all these characteristics are because the molecules are relatively far apart. At least we assume that the molecules are really far apart and moving constantly. Molecules tend to behave as if other molecules are not present, that they're just all alone floating there. And before I forget, let's take a look at the difference between gas and vapor. If an element exists as a gas at room temperature, it's a gas. If you have to use heat to turn it into a gas, then that's a vapor. Well, one of the terms we are going to discuss is pressure. Well, what is pressure? Pressure technically is the amount of force divided by the area. And you've seen things before, like if you step on a nail, it's going to really hurt, but if you step on a bed of nails, it doesn't hurt because the whole force and area thing. Atmospheric pressure is what we tend to talk about. It's the force exerted by the atmosphere on a given surface. And there's lots of different units for pressure, and I've listed them right there. Our book mostly focuses on atmosphere, ATM, maybe torr. Just an FYI, there is a thing in the book somewhere, I'll have to point it out to you in class, where you can look at all these different terms and do all the conversions, which I also have listed on this slide, but there is a handy chart in the book somewhere. And barometers are what measure air pressure. Let's take a look at the various gas laws. First up is Boyle's law, and Boyle's law just relates pressure to volume. Basically, that the volume of a fixed quantity of gas maintained at a constant temperature is inversely proportional to the pressure. If volume goes up, pressure goes down. And I always think about like this little kid with the balloon. If you squeeze the balloon, pressure went up. What happened to the volume of the balloon? It went down. Or think about a sponge in your hand that you're squeezing really tight. Well, if you release some of that pressure, doesn't the sponge get bigger? There's your relationship. Charles's law. He related temperature and volume, and basically that if you increase the temperature, the volume will increase. Now this is assuming that you're keeping pressure constant. And by the way, that V is proportional to KT. K is just some constant. But think about a hot air balloon. We put hot air in the balloon, and what does the balloon do? It expands. Next up, Avogadro's law. He related quantity, or moles, to volume. And basically that if you have more moles, you have more volume. Basically all is what he said. And assuming that temperature and pressure stay the same. But he basically was thinking about the fact that if you have a container and there's suddenly a lot more molecules in there, aren't there more molecules hitting and moving around and expanding? Yeah. So as you have more moles, your volume's going to expand because you just have more moles constantly banging into each other and they're spreading out. Then we have the ideal gas law, which relates everything. PV equals nRT, P is pressure, V is volume, N is moles, R is an ideal gas constant, There are several of these in the textbook. Just really pay attention to your units and pick the right R value. And T is temperature, must be in kelvins, not Celsius. Remember, Celsius plus 273 gets you Kelvin. The assumption with the ideal gas law is that gases are behaving ideally. They don't interact with one another. Their volume is so small that we claim they don't take up space, which obviously isn't true. By the way, page 408 are where all those different R values are. And we also do standard temperature and pressure, as you can see on this screen. Through the wonders of algebra, you can combine some of these equations, so let's take a look at them. The first one relates pressure and volume, P1 V1 equals P2 V2. You could relate pressure to temperature, or you could relate all three of them, the combined gas law. So sometimes, all you need is one of these very simple equations. Now remember, temperature has to be in Kelvin, and the reason why is because temperature is in the denominator. Well, you can't have 0 in the denominator, and you do have 0 degrees Celsius. 0 Kelvin, we've yet to hit that. That's the theoretical point at which all motion stops. So this is why you must be in Kelvin so that there is no 0 in that denominator. So what are some of the applications to the gas laws? Well, if you have density and you have molar mass, you can make all sorts of calculations. So take a look at these equations. Density is the number of moles times the molar mass divided by volume. And that should make sense to you, because what's molar mass? It's grams per mole. And if you multiply by mole, you just get grams per volume, mass per volume. And then the other one does the same thing for you. That is pressure, molar mass, and then R would be the correct constant, and T is temperature in Kelvin. Or what if you're looking for the molar mass? Density times RT and P. And just play with the units and see if you actually get molar mass, see if you actually get density. I bet you can get those units. But you do need to know that density depends upon pressure, molar mass, and temperature. The more molar mass, the more pressure, the more density. Think about more molar mass. Do you want a mouse to sit on you or an elephant to sit on you? Elephant's going to have more pressure. As temperature goes up, density goes down. Now, if you think about that with gases, as the temperature goes up, they have more energy. They're moving faster, they're spreading out. So the volume increases. And when you have volume on the bottom of a fraction and that number gets bigger, your overall answer gets less, so density goes down. And think about the application to storms. Hot air rises, it's less dense, cold air sinks, and this is what creates those cumulonimbus clouds, the thunderstorm clouds, and what can also lead to tornadoes. And you can't talk about gases without talking about mixtures and partial pressures. Very simple. Dalton's law of partial pressures basically states that the total pressure is made up of all the individual gases. So if you know all the individual gases, you add them up and you get the total. Pretty simple. And if you do some substitution and a little bit of algebra, you can get that fancy little equation right there. And it's just another way to relate pressure to moles, to RT, and volume. Not a big deal. But one thing I do want to point out in all of this slide is the N1 over NT. We often refer to that as a mole fraction. And instead of writing N1 over NT, number of moles per total moles, we just write it as X. And that simplifies some of these equations. You may or may not need these in your problem sets. I don't recall for sure, but I just wanted to show you a little bit more what you could do with some of this. Let's review the kinetic molecular theory of gases. Number one, gases consist of large number of molecules that are in continuous random motion. Picture gas particles like a bunch of little kids hyped up on sugar at the park. They're all over the place. The combined volume of all the molecules is negligible relative to the total volume of the gas that is contained. In other words, they just assume that gas molecules really don't take up space, but they do. But in an ideal situation, they don't. Attractive and repulsive forces between gas molecules are negligible. Again, in an ideal gas, we're going to assume that the molecules don't experience any attractive or repulsive forces. They're just moving in a straight line, trying to get to a wall, bouncing off, and they just keep going. Energy can be transferred between molecules during collisions, but as long as the temperature is constant, the kinetic energy doesn't change. You guys know that if you drop a ball on the ground, it's going to bounce up, but it doesn't bounce back to the original height because there is some energy lost, in quotes, between the ground. You've got sound, you've got friction, you've got heat. So when the molecule hits the side of the container, we know that there probably is some energy, quote unquote, lost, but we're going to assume it's not. And the last one is that the average kinetic energy of the molecules is proportional to temperature. More temperature, more energy. They're going to be moving harder, faster, hitting that wall harder. And so just think about what pressure means. Pressure literally means gas molecules colliding with the walls of the container. Depending on how often they connect with the wall of the container and how hard they hit is what affects pressure. So if the temperature goes up, they're moving faster, they have more energy, they're going to collide more often and harder with the walls of the container, so pressure goes up. We will look at this next one in detail in one of our Pogles, but one of the things you're going to find is that when we talk about the distribution of molecular speed, we're talking about the average molecular speed. Even though you have a container with the same gas molecules, they're not all moving at the same speed. There's a range of speeds, and we're going to take a look at that again in one of our assignments. But things I want you to think about, and I've already mentioned these, but let's just go over it again. If you increase the volume, the pressure is going to decrease. And another way to think about that is if suddenly you increase the container, it's huge. Well, now, don't those gas molecules have to move further and further and further to hit the walls of the container? So they're not colliding as often, and that, of course, decreases pressure, because what's pressure? Molecules hitting the walls of the container. And as temperature increases at a constant volume, the pressure increases. Well, molecules are moving faster, hitting the walls more often with more energy. Let's quickly review the difference between effusion and diffusion. In both cases, molecules are moving from an area where it's crowded to an area where it's not crowded. But effusion is where gas molecules have to escape through a tiny hole. So imagine you've got like a beaker and there's something in the middle dividing the beaker in half. And you've got a little hole in that divider. And all the gas molecules are over here. Well, they have to go through that hole to get to the other side. Diffusion is just molecules moving from crowded to not crowded. That's it. There is a way to find the speed of a gas molecule, and you can use that equation right there, where R is, of course, one of the gas constants, T is in Kelvin, and M is the molar mass. In Graham's law, we did look at this in regular chemistry. Graham's law just relates the rates of two different gas molecules to their molar mass. Just notice that the rate for one, when you do the other side of the equation, the molar mass goes on the bottom. Typically, we put the lower molar mass on the bottom, which means the faster molecule is R1. Remember, the lighter, the faster. So if you're comparing hydrogen gas to neon gas, hydrogen gas is smaller, so it would be R1. The other one would be R2, and then just flip them when you do the molar mass. And don't forget to take the square root. Last slide. Real gases often do not behave ideally, and we will look at this in depth and analyze some data. But let's talk about why. Real gases do not behave ideally at high pressure. Think about high pressure. Isn't that pushing all the molecules close together? And if they're really close together, they're going to experience attractive and repulsive forces. Ideally, gases don't experience those forces. So they behave ideally under low pressure, where they're far apart and away from each other. High pressure brings them close together. They also do not behave ideally under low temperatures. Think about energy. Low temperatures, they're not moving much. So again, they're going to experience more attractive repulsive forces. If they're at a high temperature, they're moving a whole lot more, and they're going to experience less attractive and repulsive forces. Again, you can read the fine details on this slide. I'm not going to read it all to you. But how can we make better predictions when gases don't behave ideally? And that is where we use the van der Waals equation. And I've given you a couple different variations on this slide. You can also find it in a textbook. And there's also some examples in the textbook, but on page 429 are common A and B values. Basically, all we're doing here is we're making that adjustment for the pressure and for the temperature, and actually the pressure and the volume, to make it more realistic. So we will dive into this and actually practice this a few times and make it make more sense in the activities that we do. So if you have any questions, ask while we're working on things during class.